Hello and welcome back to Chapter 13. We'll be talking about more features on the ocean floor. In particular, we're interested in looking at volcanic islands. These dot the ocean floor and they're fairly common, but we don't really talk too much about them. They don't come up unless you're talking about a place like Hawaii, which is an oceanic hotspot. But other varieties of or versions of the Hawaiian Islands. Other hotspots include the Galapagos, Easter Island. Those would all be examples. Society Island, and so we'll talk a little bit about volcanic hotspots and what those sort of mean. We'll talk about atolls, which are an interesting feature that form out in the Pacific Ocean and the Indian Ocean, in areas where you have coral reefs capable of being developed, so warm, clean waters. And then finally, geos, which are an important part of the tectonic story. So hotspots are areas where the mantle is rising up from the core mantle boundary and intersecting the base of the crust. And I've already mentioned a few of these, but you can see in this map that we've got Hawaii up here on the top, or sort of central left. Here is your Galapagos. There's Easter Island, and then you can even jump out here into places like Iceland, which I already showed you. That's a hot spot, a place where a plume of magma is rising up. Coming south, you hit the Azores, and then there's a few more that even I'm not kind of terribly familiar with some of these hot spots. You'll notice, actually, there's a couple of them that are in the continental crust. There are not very many, and Yellowstone is getting studied a little bit more, but we think it's a hot spot, and it's up here, Yellowstone. We talked about that when we talked about calderas and volcanic eruptions, and then also what's a very famous hotspot over here, which we call the Deccan Plateau or the Deccan Traps. The oceanic hotspots, some of them you'll notice have one track that goes off in one direction, and like the Hawaiian Islands, it comes up to the right and up like that, which creates a chain of extinct volcanoes. And then some of them you'll notice have two sort of lines of volcanoes, and that's what these little yellow lines coming off of them are. They're indicative of the plate moving on top of the hotspot creating a volcano or a sequence of a series of volcanic centers, and we actually can sort of map those out on the ocean floor. So here's Hawaii down here on the bottom, and then there's Maui, which is the next island over here, M-A-U-I, Maui. And then after that, we'll get into all the islands. I don't have them all memorized, but we have a sequence of islands that are exposed at the surface. But all of these are extinct. So only Hawaii, the main island, is an active volcano right now. And off the edge here, we've got a small volcano somewhere out here that is growing as well. All of these other islands back here have been eroded down by wave action and by weathering, and they are now part of what we call an aseismic chain, which means they are without seismicity. So at a mid-ocean ridge, we have seismicity. At a volcanic arc, we have seismicity. But in this case, there's not a lot of seismic activity. What's interesting about this is we predict the next volcano to be sort of out here in front of Hawaii somewhere as the plate moves off in that direction. And so the hotspot stays still, and the plate moves over it. If we want to know how fast the plate is moving, we can use the ages of these islands. And I'm just going to do this as an example. It's not, it's pretty accurate in terms of sort of the distances and so on, but I'm not trying to calculate an accurate plate velocity for you, but we can sort of measure from the center of each island, and we can measure that distance. And I know the distance from Hawaii to Maui is 127 kilometers. Right, so we have distance, and we need to know time. And so I know that the island is erupting today, so we'll just give it a time of 0. And I know that the last active eruption on Maui was 1 million years ago, 1 MA or MYR for million years. And so I know then that I've got 127 kilometers per 1 million 1 million years. If I want to write that out and make it sort of more useful, I might write it out like this. Turn that kilometers into meters, so that's going to be 127,000 meters per 1 million years. So I'm turning it into meters per year, which gives me, or is equal to, let's see, 0.12. I just did the math here with my handy dandy calculator. 1.02 meters, or 0.12 meters per year. Okay, and I can then convert that into centimeters by moving the decimal. There's 100 centimeters. 100 centimeters per meter, and so I can move the decimal to 2 places to the right, and I end up with 12 centimeters per year. So you'll do this in lab, and we'll do a bunch of calculations. You'll get quite proficient at making measurements on your map and doing conversions with scales, but the idea is that we know that the plate here that is riding over the Hawaiian Islands is moving at about 12 centimeters per year, and that's consistent with a fast 1/2 of a fast spreading rate. So the mid-Atlantic, or sorry, the mid-ocean ridge that's in the Pacific is called the East Pacific Rise, and it should be a relatively fast spreading ridge. So that means the other side of that ridge is moving at another 10 or so centimeters per year, and consistent with a fast spreading ridge. Here's a diagram kind of showing what's happening here down here at the bottom, or toward the bottom. I've got this boundary here, which is our D double prime boundary, or our core mantle boundary, and we have a plume of magma rising up and hitting the base of the lithosphere, causing it to melt and then creating magma that rises up to make the Hawaiian Islands. And so off to the right we see, volcanic center 1 has formed, and the plate's going to move off to our left. As the plate moves off of the hotspot, volcanic center 1 goes into extinction, so it's no longer active, and we form a new plate out to the right, new volcano out to the right. So out here is where our next new volcano will be. At time 2 here, volcanic center 2 is now gone extinct, and it sits here. Volcanic center 1 is even eroded further, so it's even now below the ocean, below the ocean floor, and we end up with volcanic center 2 showing up as this sort of inactive mountain, and then we have volcanic center 3, which is developed, and then eventually volcanic center 4 sort of show up out here in the future. Okay, here's a map of Pacific Plate hotspots. These are the aseismic ridges that I talked about, and you'll notice there's a bend in all of these ridges: Midway Island, Easter Island, and actually the Hawaiian chain. We call it the Emperor Seamount chain. That bend is indicative of a change in the plate vector, and so in this case, the plate's moving off to almost towards the west currently, but it used to be that it was moving off to the northwest, and so these are indicative of a change in the motion of the plate itself. Okay. When the islands go extinct and there's no more volcanic activity, it gives them a chance to do a couple of things. One of them is to cool off, and as they cool, they're going to show an increased density. And that increase in density is going to allow them to sink. The other thing that's going to happen is that because these rocks are formed in the Earth's interior, and that's where they're stable at low pressures and temperatures, such as at the Earth's surface, they're unstable, and so waves are going to come in, and those waves are going to cut off the top of the island and flatten them out. A flat-topped seamount, a flat-topped volcano like Hawaii is a seamount that's literally just grown up above. I'm drawing this above the ocean's the ocean surface level. That is, as a seamount, when it gets cut off like this, and this is an example down here. When it's cut off, it forms a guyot, and the guyot was what was sort of mysterious to Henry Hess, as he was mapping the ocean floor. Flat top mountains are not typical, and so he sort of hypothesized that the geos were once above the level of the ocean and had been eroded down, and used the geo as a line of evidence to support movement of the ocean floor, even though it was pretty slow and not something they could track at the time. These also can form interesting things called atolls, and these are, again, seamounts that have gone extinct. And so what happens in step one here, you have your active volcano, and you have a small reef that forms here. So you're talking about forming in tropical regions, warm waters, shallow waters where the reef can form. But the amount of volcanic activity that's going on tends to suppress reef growth and keeps it pretty small. Also, because it's still hot, the volcano is buoyant, and so it's staying up high above the level of the ocean, and it's continuing to have sediments, tephra ejected during eruptions, and it's growing and sort of outpacing the erosive power of the ocean. However, what will happen as it becomes extinct is it will sink down, and as it does, the reef will grow upward. So coral reef requires sunlight, requires there's a kind of bacteria that need photosynthesis to produce carbohydrates, and some of that is shared with the coral. And so in order to survive, the reef will try to grow upward and stay close to the surface of the ocean where it can receive sunlight. And so as the volcano sinks and gets eroded away to some degree, the reef will grow upward. And so what ends up being left is this circular island called an atoll. And I'll show you one that's already formed. So in the center of this example is your extinct volcano, and this is your coral reef, essentially here and here and here. That's your atoll. Here's the Society Islands, which are in the South Pacific. Here's an example of a place where you've still got the volcanic element present. So the volcano is here. You can see it in green as I'm outlining it in dark green. And so that's actually land, right? And then offshore, a lot of this is underwater. You can actually see the reef as it's growing, right? And staying near or at the ocean's surface. And eventually, this volcano will sink down below the level of the ocean, in theory, and all that will be left with here is the reef, the circular reef, and that's our atoll. All right, so just a few things that we see on the ocean floor. Atolls and geos are very interesting. They dot the ocean floor. There are thousands and thousands of them down there. In particular, we're interested in some of them that create these tracks called hotspot tracks, which last for a long, long time. So the Emperor Seamount chain is at least 55,000 years. So that means that hotspot under Hawaii has been active for at least that long, probably longer. And some of the other seamounts that make some of these atolls and smaller volcanoes that maybe never reached the ocean's surface level go extinct much, much more quickly. We'll be moving on to talk about ocean sediments and ophiolites in the next segment.